Our second speaker is Yuzong Chen, who is a PhD student in the School of Electrical and Computer Engineering at Cornell. His advisor is Professor Abdel Fattah and affiliated with the Computer Systems Lab. His current research interests focus on efficient FPGA architectures in CAD for deep learning acceleration.
Thanks for the introduction. Hi everyone, I'm Yuzong, and it's my pleasure to share with you about my work called BRAMAC, efficient computing BRAM architectures for multiply accumulate on FPGAs. Here's the agenda of my presentation. It will be divided into 5 parts, and I will talk about them one by one. Let's start with background and motivation. Probably I don't need to emphasize too much the importance of deep neural networks. They are everywhere around us, from different computer vision tasks such as image classification and object detection, to diverse natural language processing applications in our phones such as Apple Siri, Google Assistant, and Samsung Bixby. However, the benefits of DNNs come with many challenges. First, they are very data intensive and require large memory storage for typical DNN models. Secondly, they are very compute intensive. The fundamental operation in DNN is multiply accumulate, or MAC. Modern DNN workloads are typically executed on accelerator platforms that can perform MAC operations very efficiently. A good news is that DNNs can be represented using very low precision to offer a good trade-off between accuracy and the computation cost. When we reduce the data bit width, we can simultaneously save the cost of memory storage as well as arithmetic computation. And this will bring us a lot of improvements in the computation throughput, as indicated in the left figure. This low precision requirements of DNNs also motivates FPGAs to become popular hardware platforms for DNN acceleration due to FPGA's hardware programmability that is very suitable for customized low precision computation. Now let's look at some related works about FPGA architectures for low precision multiply accumulate on FPGAs. The first approach is to enhance the logic block, which is the most ubiquitous resource on FPGA. For example, Botros et al. Proposed 3 logic block enhancements that can implement more efficient MAC in soft logic. We can also change the existing DSP block to implement more efficient MAC. For example, these 2 works, they proposed to fracture the high precision DSP multiplier into more low precision multipliers using the same area. And another very interesting approach, which is also the focus of this work, is to add computing in memory capability to the existing DRAM and change it to a processing element. For example, these 2 works, Wang et al., Arra et al., they proposed CCB and COMIFA respectively. By the way, COMIFA was the Best Paper Award winner of last year's FCCM. They added processing elements inside DRAM to support bit serial computation. And later in my presentation, I will compare our proposed computing In-BRAM architecture, BRAMAC, with both CCB and COMIFA, as well as the DSP works mentioned just now. Let's look at the BRAMAC design, starting with its overall architecture. So BRAMAC was modified from Intel's M20K DRAM that has 128 rows by 160 columns, true dual-port SRAM, with a 4:1 column multiplexing ratio to give us 40 bits output data, as indicated by the red arrow and the blue arrow. To support computing in-memory capability, we add one additional SRAM configuration cell to set the mode of BRAMAC during compilation time. The mode can be either memory, MEM, or computing in-memory, SIM. During the SIM mode, BRAMAC can compute 2-bit, 4-bit, and 8-bit MAC2, which is defined as 2 MAC operations simultaneously, P equal to W1 times I1 plus W2 times I2. And for better intuition, I encourage you to think W1, W2 as weights and I1, I2 as input activations for deep neural networks. To start a MAC2 operation, the main BRAM will first read out 2 40-bit vectors containing W1 and W2, and they are sign extended by a sign extension marks to 160-bit. This is to prevent overflow during the bit parallel MAC2 operation. And simultaneously, a SIM instruction will send 2 inputs, I1 and I2, to an embedded finite state machine, EFSM, as shown in this figure. Later, I will go back to this point again to show that it will allow both Turing-based linear acceleration and persistent deep learning acceleration. After sign extension and sending the inputs, we will copy these W1, W2 vectors to a dummy BRAM array, which can perform chip add and shift operations using this precision configurable adder So this allows us to compute the MAC2 operation inside this dummy array instead of the main BRAM. So this will bring us a significant benefit. We can see that from this figure, BRAMAC's new added circuit blocks, which are orange shaded, they are totally decoupled from the main BRAM. So we can control them using just the finite state machine, the embedded FSM, and without interfering with the main BRAM. I will go back to this point again later. So now let's see how does this dummy array compute MAC2 operation. So basically it adopts a hybrid bit serial and bit parallel data flow as indicated by this algorithm. You will see a lot of details now, but don't worry, later I will give you a detailed example about how this dummy array works during this MAC2 operation. So this dummy array has 7 rows by 160 column, true dual-port SRAM without column multiplexing. Each row has a dedicated functionality indicated by its name. And this highlighted row, P, stores the MAC2 results for the current MAC2 operation. The first to the fourth rows store a lookup table to allow us to generate a partial sum during each input bit streaming process. So for example, if the current streamed input bits from I1 and I2 are 1, 1, as indicated by this blue text, then the partial sum here is just the W1 plus W2. If they are 0, 0, then we just select the 0, which is the first block of this lookup table. And the next row, inverter, stores the temporary inverted value generated by the input MSB. This is because that the input's most significant bit, MSB, represents a negative value for two's complement representation. Of course, we can skip this phase if the input is unsigned, which is because of most activation functions are just a review. The last row is very interesting. It's an accumulator to allow wide accumulation of multiple MAC2 operations to form a large dot product. We can see here that the cost for accumulation in BRAMAC is just 1 row of SRAM. While previous two competing BRAM architectures, CSP and COMIFA, they use n rows in the main BRAM for n bits accumulation, and this n can be as large as 27 for 8 bits MAC precision. Well, this will lead to significant main BRAM wastage for storing this temporary value. To summarize the benefits of the proposed dummy array, it has 4 rows storing a lookup table to allow efficient partial sum generation. It has 1 row storing the inverter to allow computing MAC2 with two's complement representation. It also has 1 row storing the accumulator to allow wide accumulation of multiple MAC2 operations. Now let's look at an example about how the dummy array works during a real MAC2 operation. So let's consider an example of 4-bit matrix vector multiplication. The matrix size here is 2 by 2, the vector size is 2 by 1. During the initial 2 cycles, we will copy the first matrix column W1 and the second matrix column W2 from the main BRAM to the dummy array through a sign extension mux. And this mux will extend each 4-bit value to a 10-bit value to prevent overflow during the MAC2 operation. And I encourage you guys to check our FCCM paper for more details about how to design this sign extension mux using circuits. In the next cycle, we will pre-add the copied W1 and W2 to obtain W1 plus W2. This will prepare for the next binary subtraction, and this will give us the lookup table for partial sum generation. And simultaneously, we also need to initialize P, which is the result of the current MAC2 operation, to 0. In the next cycle, we start the input streaming process. We stream in from the most significant bits. They are 0, 1. So we select W1 as our partial sum and add it, we invert it to prepare for a binary subtraction in the next cycle. In the next cycle, we will add the inverted value to P with a carry in set to 1. This is a binary subtraction. Then we will shift left the sum by 1 bit and write it back to P, as indicated by the lines of the algorithms on the right. In the next cycle, we continue the input streaming process. Now the selected partial sum will be 0, so we add it to P and shift left by 1 bit, as indicated by the 2 lines, the 3 lines else in the right part of my slide. In the next cycle, we continue the same operation as in cycle 6, but the selected partial sum now is W2. In the last cycle, we stream in the least significant bits. They are 1, 1, so the partial sum is just W1 plus W2 in this case. And we add it to B, but without left shift this time. But wait, we have to add the current P to the accumulator, and this will allow us to support a larger matrix vector multiplication. For example, if the matrix column size here is not 2, it's 4, then we need to perform another MAC2 operation. So we need to add the current MAC2 result P to accumulator, and we can start the next MAC2 operation. And our accumulator here can allow up to 256 accumulation for adding 4-bit MAC operations. To explore the area throughput trade-off of our proposed BRAMAC, we propose two variants that have 2 dummy arrays and 1 dummy array respectively, as shown in the left figure and the right figure. The first variant, called 2SA, has 2 synchronous dummy arrays that share the same clock domain with the main BRAM. The 2 dummy arrays are highlighted with red and blue colors respectively. This one has a slightly higher area overhead. It has an area overhead of 33.8% compared to the baseline M20K BRAM, but it only degrades the Fmax of M20K by only 1.1 times. The second variant, called 1DA, has 1 double pumped dummy array that has 2 times the main BRAM clock frequency. So here, the 2 main BRAM ports will feed 2 weight vectors W1, W2 to this single dummy array for a MAC2 computation. This one has less area overhead of only 16.9% compared to the M20K BRAM, but it degrades Fmax by a higher factor of 1.5 times. But this degradation is not that important because in a real FPGA design, the Fmax is normally limited by the frequency of soft logic and routing rather than the Fmax of BRAM. In addition to these 2 variants, we propose an additional optimization, which is to control the BRAMAC using an embedded FSM. So you can see the pipeline diagram here of the 4-bit MAC2 operation that was explained before. So here we can see that the same instruction actually is only needed during the wait copy phase, as indicated by the red boxes. So after the wait copy, we don't need to send in any SIM instruction. We can only control, we can just control the BRAMAC using the embedded FSM. And as indicated by the blue boxes, now the main BRAM's write part will be free. So we can use the main BRAM's write part to load the next tile of data to allow tiling-based DNN acceleration. And the main BRAM here is busy for 2 cycles in 2SA variants, and it will be busy for only 1 cycle in the 1DA variant, as shown in our FCCM paper. Now let's look at the methodology and experiment results. For tools and methodology, we use Coffee for automatic transistor sizing of BRAMAC circuits. We use Intel coders to obtain the Fmax for the baseline FPGA blocks. The baseline FPGA here is an Arra 10 device with the resource information shown in this table. Let's compare BRAMAC with other MAC architectures for FPGA. 2 of them are DSP-Works, eDSP, KRDSP, and 2 of them are computing DRAM architectures, CCB and COMIFA. We can see that although CCB and COMIFA can support arbitrary precision due to their bit serial arithmetic, they suffer from really high latency for a single MAC operation, although they can achieve high parallelism. And the latency can be as high as 113 cycles for 8-bit MAC operation. So this will bring a significant challenge for the rate matching between computing DRAM architecture and DSP, because DSP can finish the MAC operation using just 1 cycle. If we look at the area and the frequency, although the BRAMAC 2SA variant has the highest area overhead, it also degrades the Fmax by just 10%, which is the lowest degradation compared to other computing DRAM architectures. So BRAMAC 2 variants will boost the FPGA's peak max throughput significantly, as shown in this figure for a 4-bit precision case. We can see that BRAMAC 2 variants, 2SA and 1DA, boost the peak throughput by at least 2 times compared to the baseline Arra 10 FPGA, and they can achieve higher throughput than all compared MAC architectures. And similar trends will exist for the 2-bit and 8-bit precisions. And I encourage you again to check our paper for more details. So we use general matrix vector multiplication as GEMWI as macro benchmarks to quantify the speed up of BRAMAC 1DA over CCB and COMIFA for a tiling-based computation case. So the horizontal axis and vertical axis here show the matrix row size and column size respectively. So the speed up is indicated by the color. We can see that BRAMAC 1DA achieves up to 4.1 times, 3.4 times, and 2.8 times for 8-bit precision compared to CCB and COMIFA, which is very significant speed up. And to further demonstrate the benefits of BRAMAC for tiling-based DNN acceleration, We employ it to Intel's Deep Learning Accelerator, DLA, which is a popular deep learning accelerator on FPGA, also implemented using the Arra 10 device. So basically, we replace the filter cache in DLA with our BRAMAC. The filter cache stores the model weight. And in this way, the stream buffer that stores input features can send input features to both the processing element array, PE, and BRAMAC filter cache. BRAMAC can complement the PE array to calculate different output features, as indicated by the QRAC1 and QRAC2. The speed up is very good. We obtain at least 1.3 times speed up for the BRAMAC 2SA variant for ResNet 34. So we evaluate also on AlexNet. We can obtain a maximum speed up of 2 times using BRAMAC 2SA variant for AlexNet compared to the baseline DLA. Let's go to the conclusion. Adopting low precision computation for DNN is efficient in terms of memory cost and compute throughput. This is why many people are choosing FPGA as a hardware accelerator for DNN computation, because FPGA's hardware programmability is very suitable for low precision computation. To further enhance FPGA's capability to support low precision deep neural network acceleration, we propose a computing In-BRAM architecture BRAMAC. It has a hybrid bit serial and bit parallel MAC2 data flow with a fully decoupled dummy array controlled by an embedded finite state machine to allow Turing-based DNN acceleration. To exploit area throughput trade-off, we propose 2 variants that have 2 dummy arrays and 1 dummy array respectively. BRAMAC can significantly boost an FPGA's max throughput. It achieves an average 2.1 times peak max throughput enhancement over the baseline Arra 10 device. It achieves an average of 3.1 times speed up over CCD and COMIFA for general metric spectrum applications. It achieves an average 1.65 times speed up over Intel's Deep Learning Accelerator for AlexNet and ResNet 34. That's all for my presentation. Thank you. I'm happy to take questions.